Thursday. My goal is to have maybe half of that time for you to ask questions and get caught up and stuff like that. Please make sure you're staying on top of things, but it's probably going to take a little bit more than today to finish this. Okay, but this idea is really important. We're going to maybe revisit some ideas that you saw in 1010. Make sure we're solid on those, but then we add to that quite a bit in this section, okay? So a function is a very consistent mathematical rule. Does the same thing every single time, okay? Now we've got lots of different functions, but once we know which one we're working with, it does the same thing every time. What it does is, it takes whatever you plug in. It might be a number, it might be an expression. It performs some math on it. Maybe it multiplies, maybe it squares, maybe it cubes or something like that. And then it spits out an answer. It gives you an answer back. So you plug something in and it produces an answer for you, okay? After doing some math on it, okay? And it works the same way every single time, okay? And we use function notation, and you used some of this in your Math 1010 class. We'll use function notation just to kind of emphasize the fact that we're dealing with a function. Function notation looks like this. Okay? And the way we say that is we literally say the letters f of x. Okay? The function value of x. Whatever you plug in, it figures out what the function value is for you. Okay? And f of x is the same as y. So if I write y equals 2x, I could just as well write f of x equals 2x. Okay? And we've got some nice advantages that we'll talk about here. So y is exactly the same as f of x, or better yet, f of x is equal to y. Now, the reason I like that is, let me show you. Here's the function that we're dealing with here. And I did hit record, right? Yep, so good. All right. So the function we're dealing with, we've called this function f. So f of x is x squared minus 3. And what we want to do is we want to check and see whether or not this is a function. So is this a very consistent mathematical rule? Okay. So we're going to plug in a -2. So I'm literally asking, what is f of -2? What do I get when I plug in a -2? Wherever there's an x, I'm going to plug in a -2. So I put a -2 here, and I'm going to put a -2 here. It's usually best to plug in parentheses. Okay, now on these first couple, I'll show all the work, but if I square this, I get 4, and then I subtract 3. So what's the value that I get out? I get out a 1. Okay? Now, I plugged in a -2, and what I got out was a 1. Here's why I like function notation. Because if you look at this, if f of -2 is 1, that's the point right there. Those are the coordinates. X is -2, and y is 1. Okay, there's the point right there. So let's figure out what f of -1 is. If I plug in a -1 and I square it, and then I subtract 3, I get 1. Minus 3 is -2. Okay? What happens if I plug in a 0? What's f of 0? Okay? It's going to be 0 squared minus 3, so that's going to be -3. Okay, what happens if I plug in a 3? Yep. I get 3 squared minus 3, so I end up with 6. Now here's an interesting one. What happens if I plug in an a? So what is f of a? Very good. Wherever there's an x, I just replace it with an a. So that's going to be a squared minus 3. So the weird thing about this is, remember I said normally we're going to plug in a number, but sometimes we plug in an expression. It's still just going to do some math on it. It just says whenever you plug in an a, you're going to take that, or whatever you plug in, you're going to square it, and then you're going to subtract 3 from it. Okay? So here's how we check to see whether it's whether or not it's consistent. If I plug in a 0, and let's say I change colors and I do it over here, what number do I get out? I get -3 again. Would there ever be a time that I plug in a 0 and then for some strange reason this function right here produces a 6? No? No. So this is a nice consistent mathematical rule. This is a function. Okay? We dump in x's to this function and it spits out an answer. So you put in x's, what comes out are f of x's, which would be the same as y's. Okay? So sometimes we kind of draw an analogy between a function and a machine. Okay, you put something in, it does something to it, and then it spits out an answer. Okay, so let's build on our vocabulary here. The set of numbers we plug in are called the domain of the function. Okay, so these would be in the domain of the function. The numbers we get out are called the range. And since we usually plug in x's and get out y's, the domain is made of x's and the range is made of y's. Now that's not always the case, but usually, especially if we're graphing on the xy plane, that's what we're going to be dealing with. Okay? And because we usually pick the x's that we're going to plug in, I mean, I made this table and I picked these numbers right here to plug in, we say x is the independent variable, because we get to choose what it is, and it determines what y is. So y depends on x, so it's the dependent variable, okay? And then occasionally you'll hear this word, so just some vocabulary. Sometimes you'll hear this called, whatever we plug in, we call it the argument of the function, okay? So the argument in this case was a -2. The argument in this case was an a. What we plug in, sometimes we'll call that the argument. Not very often, but if somebody uses that word or you see that in a textbook, you want to make sure you understand it. Okay, so there are lots of ways to describe how a function works. We've got a couple of other ways. We'll talk about them really quickly. Each member of the domain corresponds with exactly one member of the range. Okay? The fact that it corresponds with only one member of the range, that's that consistent part. Or if we say it in really clear, about as short as we can get it, each x corresponds with only one y. That's the idea that if I plug in a 0 today into this function, I get a -3. If I come back tomorrow and plug in a 0, I'm still going to get a -3. I don't have to wonder, hey, what happened here? Okay? So you can have functions that work with things other than just numbers. So I've got a description of a function right here. And we're going to change this to CP2. Okay? So our function is the birthplaces of all the students in College Placement 2. So you guys are all in College Placement 2. This entire class right here would make up the domain. Okay? So you guys would be the domain. So we could put everybody's name here. Okay? Let's say we're going to have Josh here. Okay? And then Colby, right? Corby. Okay? And then Jessica over here. And Amber. So let's just have them represent that. Okay, so they're the domain. Okay, so the names of the people in this class would be the domain. What would the range be made up of? Yeah, the birthplaces. Josh, where were you born? Salt Lake City. Corby? West Jordan. Jessica? Salt Lake. Now, do I need to write Salt Lake again? No. I don't need to. It's already in there. Okay. And what about Amber? Salt Lake. Okay, so we've only got 2 birthplaces here. This is totally okay. Josh corresponds to Salt Lake. Corby corresponds to West Jordan. Jessica, I'm going to draw a line here. This is called a mapping. Jessica corresponds to Salt Lake, and so does Amber. Okay, now, is this a function?
Yes.
Jessica says yes. I see a few people nodding their head no. See a couple more yeses. Jessica, why do you think this is a function?
Because you can have more than one range, you can have multiple ranges, but you can't have multiple, of the same domains.
Okay.
Does that make sense?
I get what you're going for. Yeah. Natalie?
Just kind of what she's saying. You can have 2 different domains go to the same range, but you can't have one domain go to 2 ranges.
Okay. So you can have 2 different members of the domain go to the same part of the range, but you can't go the other way around. We couldn't have this. So, Josh, I'm going to pick on you. Why would this not be okay? You can't be born in 2 places. Okay? So do you see there's a problem there with that lack of consistency? We've got to make sure that every time we plug something in, or ask a question in this case, we only get one answer out. Okay? If we came today and asked, Josh, hey, where were you born? And he said Salt Lake. And then we came back a couple hours later and said, hey, Josh, where were you born? And he said West Jordan. We've got some issues, or probably Josh has some issues, if that's the case, right? Okay, so this is a function right here. So we'd put a yes right here, okay? Again, we're dumping in names, we're getting out birthplaces. Names would be the domain, birthplaces would be the range. So let's take a look at this example right here. So this is a little bit more typically what we'd see, because we've got some X's and Y's here. So I've got this set. I've got -4, 3, 0, 4, -1, 1, 2, 1, and 3, 3. So the X's, remember, those are the domains. So I've got -4, I've got 0, I've got 1, I've got 2, and I've got 3. 3 is the first one in the range, because 4 corresponds to 3. 4 is the next one, because 0 corresponds to 4. -1, because 1 corresponded to -1. Okay, now 2 corresponds to 1, so I've got to add that there. And then I've got 3 corresponds to 3. So I'm going to draw a line to map this correspondence, and I'm going to ask the same question I did before. Is that okay?
Yes.
That is okay. Okay, because remember, it's okay for, in fact, gosh, what if all of these corresponded to 3? Would that be okay?
Yeah.
That would be, okay? But what wouldn't be okay is if I had a bunch of answers here or a bunch of answers here and I had 1 and it corresponded to a whole bunch there. We wouldn't want that type of confusion, okay? If I say, hey, what's the answer if I plug in a 1? You want to know it's -1. You don't want to wonder, hey, is it this or is it this or is it this or something like that, okay? All right, so yes, that is a function. The domain would be, and we usually use set notation, and that's about the prettiest set bracket I'm able to write, but it would be made up of -4, 0, 1, 2, and 3. And then we'd close the set brackets. I'll do that as pretty as I can. Normally it just looks like a squiggly line, okay? And then the range is going to be 3, 4, -1, and 1, okay? So there's our domain and our range. Okay, now I'm going to change colors to blue, and I'm going to ask a question. What if we added 1, 3 to this? So what if we came up here and changed the problem and we did 1, 3? Now, I already have 1 here, so I don't need to add it in the domain. I already have 3 here, so I don't need to add it to the range, but I do need to map this. So what I need to do is I need to say, well, 1 also corresponds to 3. Okay, now, the problem is not that we've got several things corresponding to 3. That's not the issue, is it? What's the issue? Okay, the issue is, like I talked about a second ago. If I say, what does this give me if I plug in a 1? Some of you would say -1 and some of you would say 3, right? And we don't like that ambiguity. We like things to be nice and certain. Only one answer, okay? So, would it be a function then? Nope, it wouldn't, okay? Now, we're going to look at why this isn't a function by looking at it on a graph. So I'm going to take each one of these points. So we've got -4 and 3, that point right there. I've got 0, 4, so right here. 1, -1, 2, 1, 3, 3, and 1, 3. Okay. Now, which x value had the issue?
1.
It was the 1, right? Okay, here's why. Okay, now, remember I said a second ago, if I ask you, what do I get out if I plug in a 1? It's either a -1 or a 3. Graphically speaking, it means this. Everybody watching? It means if you go to 1 on the x-axis, what's the y value or what's the function value that corresponds to that? Well, it's either up here or it's down here. And we don't like that. They're on the same vertical line. Okay? So most of you have heard this before. You can look at a graph and tell whether or not it was produced by a function by figuring out whether it passes the vertical line test. Okay? Vertical line test. All right, let's go ahead and flip that over. So draw a graph that's a function here and draw one that's not a function here. So graphing a function, I mean, you've graphed lots of things. We could do something really simple like this. Just draw a line. Does that pass the vertical line test? It does. Okay, what about a parabola? Yep, passes the vertical line test. Okay, what if I took a shape kind of like a parabola? What could I do with the parabola to make it so it's not a function? Yeah, in fact, if I just tilt it a little bit like that, that wouldn't be a function. In fact, anything that doubles back on itself at all is not going to be a function. Okay, and you want me to give you a really unique example of something that's not a function? Is a vertical line a function? It's not, okay? A vertical line is not a function. Now, it doesn't mean none of those things are useful, okay? We'll come across things like that occasionally, and we'll do some things in this class that are not functions. It's just that we like dealing with functions because of their consistency, okay? Those linear equations that we were talking about the other day, those were functions, okay? Except for the vertical line. Positive slope, negative slope, 0. Any of those lines, those are going to be functions. Vertical line, not a function. What we dealt with yesterday, circles, not a function. Okay? All right. So you've got some problems on your assignment where you have to figure out whether or not you're dealing with a function by looking at the graph. And that's pretty easy. Just check the vertical line test. Then you've got some where you have to look at an equation and tell whether or not it's a function. And that's where you've got to consider, do I only get one answer out every time I plug a number in? So let's take a look at this one right here. If I plug in, let's just pick a number at random, okay? Walker, be kind of nice, pick a number for us. 2. If you plug in a 2, what do you get? You get an 8. Is there any chance you get anything other than an 8 when you plug in a 2? Nope. So that's a yes. That's going to be a function. Okay? I'm going to pick this one, just so it works out nicely, so you can see what I'm talking about. I'm going to plug in a 0. So I want to know what I get out when I plug in a 0. So wherever there's an x, I'm going to put a 0. So that's y squared equals, this would just be 4. And how do I know what I get out? What's my y value? How do I finish solving this for y? Square root. Now, I think we talked about this yesterday. When we put a square root in a problem, what else do we have to do? Plus or minus. So that would be plus or minus 2. So sometimes I get out a 2 when I plug in a 0, and other times I get out a negative 2. Or in other words, I get out both. So if you're plugging in a 0, your choices are go up 2 or go down 2. They're going to be on the same vertical line. So the answer here is no, that's not. Okay, John, can you pick a number for us to plug in here? Okay, let's plug in a 4. So if I plug in a 4, I get 4 squared on the bottom. That's going to be 2 over 16, which is 1/8. How many answers did we get out? Just one. Any chance I do this work again and I get something other than 1/8 if I did it right? Nope, so that one is a yes. Okay? You don't have a bunch of problems that ask you to figure out whether or not they're functions. Most of the time we like dealing with functions, so that's what we're given. Okay? But you do need to know how to do this. Okay? And some of these are going to look a little bit weird, and you practiced a tiny bit of this in 1010, but let's make sure we're clear on this one. This is exactly what we were doing on the first page. Okay? Except for it's a different function. So again, usually it's a good idea to plug in parentheses so that when you square or cube or whatever it is, you get the signs right and stuff. So this is going to be 4 times 3, so that's going to be a 12 minus 1. So what is g of 2? G of 2 is 11. Now I want you to listen really carefully. Why did I say I like function notation? What's the advantage of having it written like this? What's that, Alex? You can see your x and your y. In other words, you can see the point that's on the graph. If g of 2 is 11, what point is on the graph? 2, 11. Okay? Let's plug in a negative 3. If I do that, I've got 3, negative 3 squared minus 1. Square that, it turns into a positive 9. Times by 3, I get 27. 27 minus 1 is, so g of negative 3 is 26. Okay, now it gets a little bit interesting. I want g of a. Said we should plug in parentheses. What am I plugging in? An a. So what do I write? What is g of a? 3a squared minus 1. Okay? Something that you need to get used to is the further you go in math, the less often you get an answer that's a number. It's weird that the answer is 3a squared minus 1, but it is. That's what you get when you plug in an a. Okay? It's an expression rather than a number. Okay? Our argument, what we were plugging in, was an expression, so we're going to get an expression out. Okay? So let's see if we can do this one. 3, plugging in an a plus 1 quantity squared, minus 1. Okay, now, are we done? You could be done. Okay, it depends on, what the instructions are and stuff like that. It would be really nice if you could quickly, based on what you learned in 1010, know what a plus 1 quantity squared is. Now, the common mistake is for somebody to say, well, hey, I can just square both of those and I get a squared plus 1 and then I'm going to multiply it by 3. Is that correct? Okay, please don't make that mistake. When you square a binomial, it literally means a plus 1 times a plus 1. So if you, I don't like this word, but if you like to FOIL, a times a is a squared, a times 1 is a, 1 times a is a, and 1 times 1 is 1. So what you get is, you do get an a squared and you do get a 1, but you've got this middle term right here of 2a, and then don't forget we've got that 3 floating out front. Squaring binomials is a really important skill. Okay, yesterday we were completing the square. So I'm going to distribute through. Here's what I've got. So that means the end answer is going to be 3a squared plus 6a, and then these two are like terms. I've got 3 minus 1, so I get out a 2. Okay? That's probably the best way to write that one. Okay, this one here is a little bit unique. We want to find out what g of 2a is, and then we're going to add 3 to it. So this is going to be 3 parentheses, something squared, minus 1. That's the g of 2a part, and then I'm going to add 3. So here's the first part, and there's just the plus 3. What am I putting right here? 2a. Okay, write down your answer. Go ahead and figure it out. When you've got your simplified answer, turn to your neighbor. If you've got 2 neighbors, check with both of them. Check and see if you got the same thing they did. And if you didn't, try and figure out why. Okay, if you square that, you get 4a squared, right? Minus 1 plus 3. So this is 12a squared plus 2. Raise your hand if you got that right. Okay, very good. Okay, this last one's kind of interesting. Not even plugging in any numbers. It's just the expression x plus h. So if I do that, I get 3. I'm plugging in x plus h, just like I did on every other one of those, whether it was a number or a variable expression. I'm plugging it in parentheses, and then I'm going to subtract 1 from it. What are we going to be careful about here? That middle term. Okay, if you memorized from 1010 that if you have a plus b quantity squared, you get a squared plus 2ab plus b squared. Should have had that memorized. Then we're going to end up with 3x squared 2xh plus h squared minus 1. Now this one looks worse than the previous problems, but actually all you need to do is distribute through and I get 3x squared. What's the next term? 6xh plus 3h squared. And then can I do anything with that 1? Not a single thing. I have 4 separate terms, no other like terms, so that's it. That's all I can do. Okay? All right, any questions? Okay. All right. So there are 3 typical functions that have domain issues. Okay? We can't, and I'm going to put this in air quotes here. Okay? By domain issue, what we mean is you can't just plug in anything you want. Okay? And you probably were made aware of these in your 1010 class. One of them is division. Okay? Can't divide by 0. That is not allowed. So if you have division, you better be careful. Anybody know what the next one is? Okay, so square roots or even roots. You can't take the even root of a negative. Okay, so I'm going to say even roots. You can't take the even root of a negative. You can't take the square root of a negative, the 4th root of a negative, the 10th root of a negative. Not that we'd want to do that. Okay, and anybody know what the last one is? I doubt it's anyone's favorite. Logarithms. Okay? You can't take the log of 0 or a negative. Okay? That's not allowed. Okay? So logarithms. So if you have a function that has division, it's not that they're not functions, it's just that we've got to be careful about what we plug in. So if you've got division, even roots, or logarithms, you've got to be kind of careful. Okay? So it says, find the domain of the following. In other words, figure out what you can plug in and what you can't plug in. And most of the time, for most functions, you can plug in anything you want. All real numbers from negative infinity to positive infinity. Okay? But if we've got one of these functions or operations involved here, you've got to be a little bit careful. Do I have division, even roots, or logarithms in this problem right here? I've got division, right? What can I not divide by? Can't divide by 0. So I want to know when 6 minus x is equal to 0. Now the easiest thing to do here is to set it equal to 0 and then move the x to the other side. So that's what would make the bottom equal to 0. Anything else would make the bottom something other than 0. So anything else is okay. So we can write this a couple different ways. I could say, everybody seen that? Means all reals. As long as x is not equal to 6. I could say from negative infinity to infinity, x not equal to 6. Okay, this is interval notation. Or if you wanted to, you could just say x not equal to 6. Okay, it depends on the book, it depends on the teacher what they like. Okay, I think this is okay right here. We'll assume that it's all real numbers unless you tell us otherwise. Okay? Now, that's kind of the long way to do it. Can you look at this and tell me what we can't plug in? 3, right? Because if you plug in a 3, you get 3 minus 3. You'd have a 0 on the bottom. So this would be x not equal to 3. What about this one? Do you have division? No. Even roots? No. It's an even power, but not an even root. And do you have a logarithm here? No. You can plug in anything you want. Pick any number. We've got about 20 people here. You could pick 20 different numbers, and every one of them is going to be okay if we plug it in. So this is going to be all real numbers. Okay, again, I like interval notation, so maybe writing it like that. If you want to say all reals, write the symbol for all reals or something like that, that's okay. Okay, any questions? Okay, how about this one? We have division and even roots, right? Okay, so what could we definitely not plug in? Just based off what we saw up above here. Okay, you can't plug in a 6, because if you put in a 6, you're going to get a 0 on the bottom. Square root of 0 is 0. Okay? So we can't use 0. And we've got to make sure that whatever this is, 6 minus x, we want to make sure that it's positive. How do you say positive using an inequality? Greater than 0. Okay, that's what we want. It can't even be equal to 0 because we already ruled that out, right? So our domain is going to be whenever this is bigger than 0, whenever it's positive. So again, the easiest thing to do. Now, if I add x to both sides, do I have to switch the direction of the inequality there?
No.
Nope. Only when we do what?
Divide by negative.
Multiply, divide by a negative, or divide by a negative. Either one of those, okay? So I get 6 on this side, and I get that. Now, that's not very nice, okay? Usually we write the x first. Now, it doesn't matter. If you read from the variable, x has to be less than 6. X has to be less than 6. The only thing I did from here to here is I just did a big pancake flip. Put my hand under there and flipped it over. So switch the side, switch everything about that, okay? Let me remind you how to graph that so we could write it in interval notation. Here's the number 6. I'm going to circle it. Should I fill it in based on this little inequality here? Nope. And which direction should I shade? I'm talking about the x's that are less than 6, so I'm going to shade this way, okay? So if I wrote this in interval notation, the answers would start at negative infinity, and where would they stop? They'd stop at 6. Round or square bracket? It is round. It is round, okay? So either one of these answers would be okay. That's how we draw a picture of it. Now let's just double check. Pick any number you want that's less than 6. Pick an easy number like 0. Isn't 0 less than 6? What happens if I plug in a 0? I get a 7 on the top and I get a square root of 6 on the bottom. Am I okay with that? You bet I am. Okay? All right, let's take a look at the next one then. Which function do I have a problem with? Division, right? If we didn't have division on here, we'd be all set. Okay? Am I worried about the top or the bottom? I'm worried about the bottom, okay? So I want to know, when does x squared minus 9 equal 0? Because that's what I don't want, okay? 3 or negative 3. There are two ways to do this. One way to do it is to move this to the other side, take the square root, and you get x equals plus or minus 3. So those are the numbers that we'd have to throw out. Does that make sense? You doing okay back there, Jeff? Okay. The other way to do it is take x squared minus 9 equals 0. And does anybody recognize this right here? What is it, Tori? Very good. You can factor. This factors to x minus 3 and x plus 3. Does anybody remember the name for this? Difference of squares. Difference of squares. And the answer that would come from here would be 3, and the answer that would come from here would be negative 3, and those are the two things that we can throw out, okay? So it would be everything except for plus or minus 3, okay? Okay, now, this looks very similar. Take a good look at that. Set it up the same way. When does x squared plus 9 equal 0? Move it over, right? Same steps. Square root both sides. Take the square root of both sides. I get x over here. And what do I get on this side? Yeah, you get an imaginary number. Technically, it would be plus or minus 3i. Not a real number. And we're usually just dealing with real numbers. So you can plug in anything you want. Anything is okay. And I want you to think about it this way. Here's why. You could figure this out just by looking at it. What can this denominator never be? Can't be 0. If I plug any number you can think of in, what's the first thing I do with it? Square it. If you square a number, it's always going to be positive. Or the very smallest it would ever be would be 0 if you happen to plug in a 0. Then what do I do with any number that I square? I add 9 to it. So I'm taking something that's positive and I'm adding 9 to it. Are we in any danger of the bottom turning into a 0? None whatsoever. So that's why the answer is all reals. Okay? Negative infinity to infinity. Any questions there? Does that make sense? Good to look at those and think about them that way. Okay? All right. So, couple things we want to remember, and I'm hoping I can get through one more example and then we'll be done. Okay? So remember, f of x is read f of x. It literally means the function value at x. So if we find f of 2 on this function right here, we're literally asking, what is the function value at x equals 2? That's what we're asking. If I say find f of 2, we're saying, what is the function value at x equals 2? What is the function value when I go to 2 on the x-axis? What do I get when I plug in a 2? Okay? Or another way to say that, because function values are y values, is what is the y value at x equals 2? On this particular one, f of 2, square 2, add 1, we get 5. So what's my y value? What's my function value when I plug in a 2? I get out a 5. Now, this is a really important idea that you understand, hey, when I plug in this number, I get out this number. Because we're going to do a little bit of that in reverse. So if you understand it forward, then you're in good shape. And if you have an ugly looking function like this, which you may or may not have seen before, you can still answer these questions. Okay? So, here's what this paragraph says. Here's this nasty looking function right here. And we want to figure out what's f of 0, what's f of, my gosh, look at that ugly expression right there, that's 3 pi halves, okay? And what's f of 3 pi. Now those look really weird, but what we're saying is if you plug in a 0, or in other words, if x is 0, what's my y value? 4. If you plug in a 0, you get out a 4. F of 0 is 4. See how you can see the xy pair there? Okay, now even if you don't remember how I said the name of this expression right here, this is the x coordinate. Let's go find it. Well, that's not it, and that's not it. Is that it? That's it right there. So what do I get? I get 0. So this one was 4. This one was 0. Let's go find this one. You find it. Write it down. Check with your neighbor. What'd you get? -4. It's right here, right? Okay. What is the domain? What is the domain of f? What are the x's that you can plug in? Here's how I describe this. If you want to know what the domain is, take the graph and squish it onto the x-axis. To take all those points, squish them down here, all these, squish them up here, and so forth. Do I have any answers over here? None. Any over here? Okay, so they start where? Start at 0, stop at 4. It's got 4 pi. Square brackets. Why do I put square brackets on it? Because those endpoints are included. Okay? Okay, if that's the domain, if you find the domain by squishing it onto the x-axis, guess where you squish it to find the range? Squish it onto the y-axis. Squish them all over here. Push them over there. Do I get any answers down here? Where do they start? -4, and where do they stop? +4, square brackets for the same reason. Okay? Now, it says list the intercepts, right? Any points where it touches or crosses the axes. So, where's the first place that it hits an axis? 0, 4, right here. Where's the next place? Okay, it's called pi halves 0. So that's an intercept. That's an intercept. Is this one? Nope. This one? Yep. This one? Nope. Yes, no, and yes. Those 5 points right there are the intercepts. Those are the ones that we'd want to list. Okay, any questions there? Okay, just a couple more and then we're done. It says, how often does the line touch, or does the line intersect y equals 2? Where would y equals 2 be? This is why it's so important to know what lines look like. Y equals 2, what type of line?
Horizontal.
Horizontal. How many times?
4.
1, 2, 3, 4. Right here, right here, right here, and right here. So the answer to that one is 4 times. Okay, take a look at this one. Are they giving me the x value or the y value? They're giving me the y value. So it's saying for what values of x does f of x equal -4? So what this is saying is, where can I be on this graph and have a function value of -4? Tell me when I'm there. Right there. What's the x value? Pi. Tell me when I'm there again. Right there. What's the x value? So pi and 3 pi. And the last one, for what values of x is f of x greater than 0? Now that's a tough question. What does it mean to say f of x, which is the same as y, where are the y's greater than 0? What is it?
All the ones that are above 0.
Okay, all the places where the graph is, this means positive, where the y's are positive. Are the y's positive here? Yes. Here? No. So we're talking about from here to here. And then again, where is it positive? Right here, here, and there. So we're going to go from 0 to pi halves. Start up again, and we use that union symbol for this. 3 pi halves. Where do I stop being above? 5 pi halves. Union, and the last one is 7 pi halves. To, where do we end up here? End of the domain, 4 pi. Okay?
Wouldn't it be only the ones above the 0?
What do you mean?
Because you're doing ones that are equivalent to 0.
Yeah, but I'm not including them. Does that make sense? So I'm using a round bracket rather than a square bracket. Does that make sense? The only place where I use a square bracket is on the very end. Right here, which is clearly above, and right here, which is clearly above. Does that make sense? Okay, think about that for a few. Okay, I kept you over. I'll make it up to you. Have a great weekend. 3.1 isn't officially assigned, but you could get started on it. It's not going to take much time for us to finish this up on Monday, and then we'll get started on 3.2. If you need to watch the videos, I upload these every day. If you find they're not there,